After my year, he left too. He's like, fuck GD.
So our first test.
He went to West Ranch.
I would too, dude. Fuck that school.
Is scheduled on Wednesday,
March 3rd.
March 1st.
Do you get the entire board with that? The GoPro? Do you get the entire board with that?
No, is that right? I'll come in on Friday.
Doesn't it bother you with your arm? Yeah.
A little bit.
A little bit.
So the first midterm we're gonna have is next Wednesday.
But March 3rd is a Friday.
No, you're good. Back
It's
first.
the first. It's the first.
It's first, am I right?
Yeah, it's the first.
Okay.
It's the first.
And I plan to cover from section 13.1 to 13.8, basically all the things in chapter 13. And the problems will be extremely similar to the homework questions we're working on my next slide. Except that there are graphing questions. You know, I will give the quadratic functions in the graph. Okay, so those ones are not tested on the online system.
I
Right?
have my arm wet. My arm's wet.
What did you do Saturday? What did you do Saturday?
What am I doing? I have class.
Oh yeah, what time you on?
I can hear at 1.
Oh, so you're out there at 4, right?
5, yeah.
Afterwards, you go to classes on this shit?
If I'm not tutoring, yeah.
You're not tutoring, like, you hang out with me.
Okay, so
I gotta make money.
Yeah, hanging out with me.
Alright.
so when we first introduced partial derivatives, I did mention its relation between the partial derivatives and the minimum, maximum, and even the second order derivatives, right? If you remember. So I want to recall the basic model of a one-dimensional case. So let's say if I have a one-dimensional function f of x. So we're interested in finding all the extreme values, where the function achieves its maximum value or minimum value. Okay, so just a couple of terminology includes minimum or maximum. And also, if you look at this curve, there are some points you can achieve its extreme value at a small neighborhood, right? For instance, this guy. And there are some points you can achieve the extreme value in the whole domain. For instance, this one. All right, so we have distinguished these two different types. So these ones, as long as you can achieve the extreme value at a small neighborhood, they're all called a local minimum or local maximum. Okay. And sometimes it's called a relative. Relative minimum or maximum. I'm not going to write down the definition as long as you already know what they're talking about. Right? So these points are local minimum. This is also local minimum. This is a local maximum, and local maximum. And naturally, we also have a definition of global minimum or maximum. So this is basically in the neighborhood. So this is also called an absolute maximum. This is in the whole domain. Okay, for instance, if I'm trying to find the global maximum, the natural candidates are the local maximum, right? So if I'm trying to find the global maximum, it's naturally coming from the local maximum. Because if it is not even a local maximum, there's no way it can be a global, right? So if I need to find a global maximum, I don't need to look at all the points on the whole domain. I just need to look at the 3 local maximum and I choose the maximum one from these 3. Right? So this guy is going to be a global maximum. And if I'm trying to find the local minimum, the global minimum, and just looking at all the local minimum and I choose the smallest one. Right? So this one is going to be a global minimum. Okay? Now with me? So these are the terminology. We have the extreme values. When I'm talking about extreme value, basically I'm talking about either it's minimum or maximum. Okay? As long as it's minimum or maximum, you have the local version and the global version. To be a global maximum, it has to be a local one first. but local maximum is not necessarily a global maximum, right? So these are very natural ideas of the definition of function value. On the other hand, we want to relate all those things into calculus, right? Basically, we're taking derivatives. So at all the extreme values, we know that tangent lines are horizontal. So basically, as long as it is an extreme value, no matter it's global or local, the derivative has to vanish, right? So the derivative has to vanish. So this is so-called a critical point. Critical point basically means derivative is equal to 0. Okay? On the other hand, as long as we can use derivative equals 0 to find all the extreme values, there's another test to tell whether it is a maximum or minimum. That's called a second order derivative test, right? So at the local maximum, my second order derivative has to be
Negative.
negative. In other words, the first order derivative has to decrease, all right? So this is the slope, if you can remember. So this is slope, positive on the left, negative on the right. So basically the slope is decreasing, all right? The slope is going increasing and then decreasing at the maximum point. So at this maximum point, the second order derivative has to be negative. So the first order derivative can decrease. That was me? Okay. So at the local minimum, the slope of the tangent line goes decreasing and then increasing. So the second order derivative has to be positive. So the slope can increase. All right? So basically, the second order derivative is greater than 0 will give you local minimum. And second order derivative is less than 0 is giving you local maximum. And if the second order derivative is equal to 0, this second order derivative test is inconclusive. Inconclusive does not say it is local maximum or minimum from this test. You can still use other tests to see whether it is local maximum or local minimum. It's just that you cannot tell it from the second order derivative test. So I want to generalize this all to functions in the form of z equals fx over 3. Okay. So this is the single variable calculus, pretty easy. You can easily see the picture. Second order derivative test and the first order vanishing test is also working for multivariable calculus as well. So I want to quickly give you the definition. So for a point to be a critical point, when you have two independent variables, okay, we have to require the partial derivatives are all vanishing. So EB equal to Fy is equal to 0. We have two first order derivatives to a point AB. If it is a critical point, then all the first order derivative vanish. Okay? And also for a point AB to be a local maximum or local minimum, basically as long as it is a local extreme, it has to be a critical point. Okay? So similarly, in the two independent variable case, if we're trying to find the local maximum or local minimum, we still take the first order derivative and make the first order derivative vanish. That was me? So basically the same thing. Here you're taking the first order derivative, you make it vanish, you find all the points. Okay? So this is the first step for us as well. And then I'm going to give you the second order derivative test to characterize the critical points as maximum or minimum. Okay? So let's quickly go through several very simple examples to see how we find all the critical points, which are the candidates for local extreme values. Okay? So this is our function. F(x, y) is equal to x squared minus 10x plus y squared plus 10y. So I want to find all the critical points. Find all the critical points. So what do we do? fx is equal to 2x minus 10 is equal to 0, and fy is equal to 2y plus 10 is equal to 0. So these two are extremely easy linear functions to solve. So I have x is equal to 5 and y is equal to minus 5. So the only critical point here is going to be 5 and minus 5. So this is an extremely easy question. The only point I want to make, okay, so the only point I want to make, and this is the very common mistake I see in the end, is when I'm looking for a critical point, when you have two independent variables, you're supposed to have a point on R2. Okay, you're not getting a value, you're not getting two values, you're getting pairs of numbers as a point in R2. Okay, so these are the critical points for functions involving two independent variables. A lot of people solve 5 and negative 5 doesn't say anything about the point. Okay, so these are only about the x value and the y value. You're supposed to put in a point in R2. This is the only critical point. So basically, throughout the whole chapter 13, you are doing derivatives, right? You're doing derivatives in different places, and they're telling you different information. Here we're using derivatives to find all the extreme values, okay? And in terms of solving this critical point equation, sometimes you're getting extremely easy questions like this one, but also sometimes you may need to do more work. So this is my function, okay? I still want to find all the critical points. So the very first step is still to take the derivatives. So fx is equal to 4y plus 4x cubed. So this guy is equal to 0. So fy is equal to 4x plus 4y cubed is equal to 0. Essentially, I need to solve this system of two equations. All right? That one is a system of linear equation. And in fact, they are quite independent. You can solve x and y independently. In some other cases, you're going to see more involved equations. Okay, so you can see linear equations, you can see quadratic equations, you can see all kinds of equations. There are different ways to solve equations. For instance, if you look at these two equations, the very uniform way is to eliminate variables. All right, so this is the solution. This is the way of solving system equations, no matter what system you have. As long as you can substitute one variable by the other one, then you can eliminate the equations. Okay? So basically, I can easily simplify these two equations into x is equal to y is equal to minus 4x cubed, and x is equal to minus 4y cubed. Okay? So this is two equations right here. So I want to do substitution to eliminate one of the variables. Which one can you do? Actually, you can do both, right? You're confused here. So here I'm just eliminating y, or if you want, this is just class is equal to 0. You don't follow it. This is equal to 0. But I needed to remove the 4 as well, right? So that's what we have. Y plus x cubed is equal to 0. X plus y cubed is equal to 0. So if you want to substitute one variable by the other, you can do both of them, right? Which one do you want to substitute?
X into y.
X into y. So you want to substitute y. You want to substitute x by y.
Sure.
Okay. So which means I need to use the second equation to get x is equal to minus y cubed. So then I'm going to use this to substitute in the first equation. So I'm having a y plus minus y cubed in cube is equal to 0. Okay? That's what we have. So regardless of what system of equations you're getting, if there's a way of substituting one variable by the other, always try that first. Okay? So always try whether you can eliminate one variable. Then you can get one equation with one single unknown variable. Okay? So we can solve this equation by y minus y to 9 is equal to 0. And we can indeed factor this equation. Okay, so it's going to be y 1 minus y to 8 is equal to 0. So the solutions are either y is equal to 0 or 1 minus y cubed, y to 8 is equal to 0. Which means y to 8 is equal to 1. And these x, y's are all real numbers, right? So x, y's are all real numbers. So the only possibility for a number raised to its power is equal to 1 is either it is 1 or minus 1. Right? 0 raised to its power is not going to give you 1, right? So I have a solution coming here and two solutions coming from here. So y is equal to 0, 1, or minus 1. Okay? If you're not fully convinced, you can actually factor this thing. You can indeed factor 1 minus y to 8 by difference of squares. Okay? So you can indeed solving this equation by going even further. So y 1 minus y to 8 is in fact equal to y 1 minus y to 4, 1 plus y to 4. So here I'm using the formula of difference of squares. So this is 1 squared minus y to 4 squared. All right? So this is actually y 1 minus y to 4 squared. So that's why I have 1 minus y to 4 plus 1, I'm sorry, multiplied by 1 plus y to 4. All right? I can indeed go further because this is the difference of square again. So I can do y 1 minus y squared, y plus y squared, then y plus y to 4. So I can even go further for 1 minus y squared, right? So this is going to give me y 1 minus y, 1 plus y, 1 plus y squared, 1 plus y to 4 is equal to 0. Okay? So if I look at the multiplication of 5 different factors, 1, 2, 3, 4, 5 different factors, I know y is a real number, so this guy is definitely positive. It's never going to be 0, right? This is also positive. So the only chance for the multiplication, the product of 5 factors to be 0 is y equals 0, y equals 1, and y equals minus 1, all right? So this is how you, strictly speaking, solving the equation. So I get y is equal to 0, 1, and minus 1 coming from these 3 factors, okay? Or if you prefer